even showing something that just verbally we'll try to explain first, and then we'll go into something. So see, suppose you have you have plane geometry, yeah? Like a wing geometry, for example. Now, well, wing geometry wouldn't be the best example. Let's say you want to simulate like a artery in your group only. Okay? Artery. So now you want to simulate only, or you want to create blocks only where the artery is and not anywhere else, because the artery will be hanging in space in a curved way, and there will be a lot of empty region outside the artery which doesn't lead to a result. There's no flow going on outside the artery. It's always inside the artery, right?
Correct.
So for that purpose, you can use this brush called geometry brush. Geometry brush basically does this, that wherever there is a geometry and if there is a brush is basically a bounding box kind of region. There can be a list of brushes you can use to chalk out multiple different regions. So you can specify a brush overlapping with a geometry region, like surface of a geometry, and the brush contains not only the bounding box but also the resolution you want, or the resolution level you want in a multi-resolution case. Okay. So, see, the geometry brush technically, well, for a single resolution, it will be just one single 0 level resolution. That's it. So wherever you apply the geometry brush, only if, for example, if you send the geometry brush at all, okay, then the list will basically create, this STL2 marker will basically create a series of blocks wherever the geometry brush has been defined and wherever there is a surface that has been found. So any block which might contain a geometry surface and there is a geometry brush bounding box which contains that block,
okay,
that block will be created. So basically the conditions are, algorithmically the conditions are, create the block if the block might intersect with any triangle in the given STL, and if any of the brush's bounding boxes contains this block or intersects this block as a common area with this block.
Okay. So it creates new blocks over there, and then according to the resolution you pass over there.
Yes. Okay. And area brushes
for like internal flows, is it?
No, it can be used anywhere. It means basically
anywhere
anywhere. Basically, it will create. See, there might be cases where you have weird geometry, but you only want to simulate some part of it. Okay. Then you use a geometry brush and you use the bounding box such that you single out only that zone of the geometry surface where you actually want the blocks. The remaining geometry will not have any blocks, no simulation.
Any blocks? There won't be any blocks allocated there. Yes. Is what you're saying, right?
Yes,
okay.
Yes.
So
or
then
created also.
Not created also. Okay. So then geometric process area brush, is it like can you give some? It can be any 3D shape, no? Like it'll just see where the blocks intersect and then does it do that? Like it could be any general surface. Like
the most general surface is STL surface, which is just a collection of triangles. It will basically look at where like it will basically the algorithm goes like this. Over all possible blocks, I'll go to each possible block. Suppose my grid is empty. I'll go to each possible block. Then I will see if I had created this block, would any triangle have intersected from the STL? Okay. If so, then also check if any of the user provided geometry brush bounding boxes intersects with the volume of this bounding box of this block. If both these conditions hold true, then that block will be created and created. If you're sending a marker, then that will allocate also and do the marker discretization there also.
Okay, and area brush is just simply bulk refinement.
Area brush is basically, it will only that geometry condition will be taken out. So basically, any block which has an intersection with the bounding boxes in the area brush vector, those will be created. So these can be used to resolve the wake behind a car, where technically there is no geometry, but still you want a high resolution or something, or at least some block created. So by default, if you are doing a full external flow, you will, and a single resolution thing, technically, you can create all the blocks in the domain and delete only the blocks which are there inside the geometry. That is one way. That is actually the best way. The other way is you try to segregate all the external regions into small cubes and pass that list of cubes as area brushes. And the surface of and the bounding box containing the STL as the geometry brush. But the best way would be for single resolution it doesn't matter much because well, it will matter in your case actually. There you will be heavily using geometry brushes, not and a little bit of area brush.
Yesterday I
So
used both of them the brushes and it gave me the desired.
okay, yeah. So basically that's the thing. So see, if you use only area brush, no, or only geometry brush, and suppose your geometry has a big hollow region, huh? It is very much possible that the blocks will happen on the surface only, and the internal or the external won't get created.
Oh,
So for the internal regions, you have to create a separate area brush because internal to the area brushes are important for creating brushes where geometry is not there, creating blocks where geometry might not be.
so area brushes are for removal and they are for creation.
Area brushes are for removal.
Ah,
No. Area brushes will create blocks where there is where you can't use a geometry brush because there is no geometry. Okay,
oh,
let's see
okay.
with examples.
Oh no. Now I understood. Understood now.
So it
So
should be
that
called the empty region brush or something like that, where there is no
okay.
geometry.
Okay, so I basically needed only geometry brush and no area brush. I used area brush and it is creating outside the geometry also. Okay.
If you want
Ah,
outside the geometry, away from the geometry, you can use area brush.
that is why the way I created yesterday. So it is having very heavily resolved solid region, which I don't want
Okay, okay.
because I defined the area geometry over there, the area brush over there.
Okay, okay. So we'll take some examples and check. So I guess since this is optional, only 7 people or 6
So
people.
I will have to leave in some time. So,
Yeah. So no, so let's quickly finish up this thing.
So basically, Samidip, geom brush is same as area brush. No, it's just it's just that you're giving that surface for the geom brush.
Extra
And it's only
condition,
allocated.
yes.
So
It's one
otherwise, the
extra
principles are the
condition.
same, right? Both.
Yeah, principles
Yeah.
are the same. Yeah.
Okay. You're giving the 3D surface in the most general sense. Okay. Where it
Yes.
will.
So let's take an example and check. So okay, we will try to write. We try to close all these other things, and we'll see what this STL2 marker actually. So STL2 marker, if you really want a simple example, instead of directly starting with the example file, because there it tries to be a bit more general. That's why it looks a bit complicated. It's not that complicated. So we'll go back to thermal, and let's see what was the status we left it in. Okay. Tests. So, out status. So we will, by the way, this app, what did we change an app? Oh, we tried to do some fancy things here. Okay, let's start the app. We'll do it in the test only. So app, I think we can CMake build. Oh, yeah. CMake minus build. revert back to index.hpp. So sorry, 12:10. Right. So now that this is done, we run the grid branch, where we were trying to domain decompose a grid, which we sort of did, right? We took a block. We did not parallel domain decompose using MPI, but we decomposed using blocks. Okay, so we will close that for now. We will start afresh in a new branch. So we'll add status the scalar block is also running, right? Like, so what we can do is we can commit this also as a test case. Huh? So for that, we will need to download the wget this thing into one of our locations. So how do we do that? Or let's not, like, it's okay. If we have time later, we'll see. Right now, let's quickly finish up the main part which is required. Remaining fanciness we'll do later. So here we decompose using blocks. Go here to kernel break, and we have a merge request already. So we will mark it as ready and merge. Okay. So once it is merged, we will take out the pipeline, take out a branch from main where we will try to create. Okay, let's check examples only, how to quickly create. If you really want to, so using STL to marker. And this we should take from branch, but it'll take a bit of time. Okay, fine. Let's create from main. They will merge it later. There shouldn't be any conflicts per se. So 13. So git checkout main, git checkout, git pull. There won't be much of a difference. Git checkout 13. So we'll create an example in tests only. So test STL to marker. So it's clear, right, what a marker is for people who are not familiar with this term, what marker might be. So that basically is that you are given a CAD geometry, which is just surface representation, like as we showed previously in the assets, that thing. SLABS core, examples, assets. So if you take a cylinder, for example, this will look like, this is a surface representation. If you take the wireframe view, you'll see only the surfaces are there. And then how do you discretize this onto, so how do you do a volume rendering of this onto a grid? I discretize it into, to a grid such that all points have a grid, volume grid points have a value 0, 1, 2, 3, depending on which region of the surface it belongs to. See, a surface can have multiple sections. So if a particular surface has, suppose the geometry is like, 2 cubes attached to each other. So then there will be total 3 regions. One is outside all this business. One is inside cube A, another is inside cube B. So you'll get 3 marker ADs or 3 different types of clusters of points. Okay. So that's the basic idea. So now how do you use it? How do you generate markers from which can be used for LB simulations and things like that? So you will call grids because you need to create a grid of these markers, points, and our block also. But grids. So then we'll just call int main. So suppose I want to open up a STL file. So first I'll call. So usually you can read into memory a STL file by calling this thing called STL holder, which is there in SSLABS CAD. What it does is it essentially from the text file that contains the STL triangles, it will create an in-memory data structure containing the STL triangles. So you can iterate over it very nicely and so on. Otherwise you have to keep reading line by line and so on. So we'll pass the file which we want. So let's pass that using command line argument. So std.
I just got this one. So the STL is basically a list of those normals, right?
Triangles. So I'll just show you, open up an STL file and show you how it looks. So let's see, it's a cube. So first, let's see what the cube looks like in real, like in principle. So you open up a view, cube. Sorry. This won't say anything. STL. So you see this is a simple cube. And if you look at the surface wireframe representation, it's just a collection of triangles.
Yeah.
And if you look at the STL file, it just says, okay, you see this recurring pattern, like a group of 3 numbers, and then, so this is called the normal to the facet. So a facet is the face or a triangle section. Okay? A triangle is called the facet basically in here. And it will give the normal to the triangle first, although half of the times these normals will actually not be correct because it depends on the software which generated it. And the second thing is there are no consistent conventions usually, that it's always outside facing, always outwards, always inwards or something like that. But people say, okay, it depends. It's best to recalculate the triangles once you get this according to your own conventions. Then the next ones are vertices. So these are the 3 coordinates representing the 3D coordinates of the 3 vertices of the triangles. This is one triangle information basically.
Right.
And then it's another triangle. So like this, there will be some n triangles like this. That's it. That's STL file.
Got it. So any complicated geometry is patched with triangles.
Yeah. That is mathematically also that is the simplest what do you say? Discrete representation of continuous geometries or biometric shapes you can get in 3D. In triangles.
Oh, is it? Okay.
Yeah.
Oh, okay. Nice. Okay.
Missing.
As in, what will happen if? Oh, okay, I'm just asking. Like, what would happen if you use rhombus? Let's say.
See, a rhombus is a 3D shape. So you can't create a surface representation in 3D using a 3D shape. You have to use a 2D shape to create it.
I mean, like.
Rhombus also 2D. Okay. Oh, so sorry. I keep thinking of rhombus. It's hedral things.
Okay.
Yeah. Oh no. See, you can make a triangle is the simplest. Rhombus also you can create using 2 triangles. No? So
2 triangles.
Yeah.
See, no, that's okay.
Yeah. So it's not the
triangle is the smallest. Yeah.
Triangle is
okay,
the
like
smallest.
that.
Yeah.
Okay, like that. Okay.
In 2D also it is the 3, 4. In 2D also it is the smallest shape which can tile a surface or something.
Oh yeah, makes sense.
It follows that you need 3 points to define a plane, right?
Yeah. Exactly.
Oh right. Okay.
So we will just pass the argv one argument straight from command line. Gc r star. By the way, do you know if you just put argc, what will happen? Suppose I am too lazy not to put argv also. It will not compile because the main function in any C code either expects 0 arguments or 2 arguments of the form int and r star list. Okay, so usually by default, this will read the STL file, but depending on what the units are in the STL triangle, of the STL triangles in the STL file, you can scale it up, scale it down according to your convenience. So for example, whatever representation of the decimal numbers are there in that STL file for the triangles. Suppose those are in millimeters. Huh? So it's like 100 millimeter, 150 millimeter, and so on. But your simulation is happening in meters, SI units. Okay. Then what you would like to do is, I would like to scale it to meters. So essentially, whatever the units are, or whatever the numbers are in the triangle, you will want to multiply using 1 to the minus 3. So basically, this second argument gives you that option, that STL units. You can pass where STL units are essentially real coordinates. How do you want to scale each axis? So SSLABS R chords. It's in 3D. So constant ST size equals 3. Like this you can do. So that will basically, internally when it is reading up the triangles from the file, it will automatically multiply by 10 to the minus 3, all the vertices. Will become in meters. Just give me 1 minute. Huh? Let's get this up. Yeah, sorry. So let's get back to this thing. So we were trying to convert this triangle, whatever it was, into our own STL unit. So suppose we'll keep the same units that the triangle currently has. Usually this is not a default parameter because it's better to keep in mind that what units you're converting back and forth between. Like if I make it implicitly equal to 1, one day you will miss using this argument, and then whole simulation will try to, what you are trying to simulate a meter long wing, you'll end up simulating a millimeter wing or something like that. Okay, so that will be a problem. So this basically takes the triangle into a STL holder. Or you can, all the CAD functions currently in core also allow you to directly use the file name itself in the as reading into the CAD functions. but it's better to use STL because then you can do a lot of manipulation on the STL also. Like for example, in this STL, you can loop over the triangles saying that, first of all, tell me what all patches are there. So again, you will get a pairwise element which says STL patches. Patches basically means in a STL file, there might be multiple groups of triangles, okay, with a named patch. So this patch pair that is returned, the first one of that is called the patch name. Name is basically p dot first, and the second argument is the vector of triangles. So then you'll get a vector of triangles. So this one will be a triangle from p dot second. So p dot second is a vector of triangles. From that vector, you're trying to now loop over every triangle in that vector. And then every triangle has a vertex 0, vertex 1, vertex 2. So if you want to list down all the vertices, then you can say that, so I'll call this new triangle or something, just to demarcate it. Or I can, instead of new triangle, I can just say draw a line. It's a new triangle. Okay. And I'll loop over the vertices of the triangle. So, or instead of looping over, let me just see only, so look nicer this way. Vertex 0. So this is how it looks like. Now basically what I'll do is I'll quickly run this code, and
I mean, that is STL holder, right?
yes,
Directly,
SSL holder, yeah. Sorry, I missed your question. What was the question?
no, in that STL dot patches. So, is it STL, that is STL holder, no?
Yes, that is STL holder, yeah. So in STL holder, the hierarchy is inside the STL holder, there is a mapping patch name to a list of triangles, and then you can iterate over the triangles.
Okay.
So basically, internally, STL holder is basically this kind of data structure: STD map, STD string representing the patch name, and then there is a STD vector of SSLABS triangles.
What is the difference between holder and parser here?
Okay, good question. So holder basically uses parser in between. So if you suppose want to, okay, how would you do parser? So let's see, STL parser, parse, okay. You'll send the file name again and STL units, same kind of arguments. Here, whenever you iterate over this thing, no, parser. So I think the iteration format is first of all this. As long as it is not completed parsing, you continue, and then you start calling in the triangles, like how is it called? Get triangle or something like that, right?
Get triangle.
Yeah. So this will be your triangle variable. Okay. Get normal also is there and so on. So here, every time you call this parser, no, this parser get triangle, and this parser dot completed, it will again start reading the list, the file directly. Here, STL holder will read the file internally once and store it in memory. So next time you can do multiple calls to this for loops over STL holder, and all of them are happening directly from the in-memory triangles in a data structure. So they're very fast. It's RAM to cache, RAM to cache. Okay. Here it is hard disk to RAM to cache every time.
So it's not in the memory when you create a parser.
This is not in memory. Okay. So initially when we were doing it, it was like, okay, you use STL reading only once at the very beginning of the simulation. So it's okay. But if you really want to, just 1 minute. Yeah, if you want to do it multiple times instead of only at the beginning of the simulation, then I think STL holder is the better option. Okay. The second thing is there are many cases where you want to suppose modify STLs. You can either use FreeCAD and all those things to do it, but here you can do your own thing because you're getting access to all the vertices. Once you can modify triangles also in the STL patches. So what you can
No,
do
okay,
is
so there is one shift function also, and then it's used for rotation also. I use it, but I did not get the difference between parser and folder antenna.
this is
Now I got it.
okay, fine. Okay, sure. Basically, this is a slower one-time use cousin of STL holder. So basically, if
also
you're
use parser, but only once.
yes,
And then
in-
stores.
yeah. So that's why we're basically trying to phase out that STL parser slowly, deprecate it. STL holder will become the standard. But currently, all the CAD functions take in both arguments, alternate equivalently, STL holder, STL parser, or STL files directly. Okay. So let's iterate over triangles. Let's see what it will do. We were trying to do something else here. No, nothing. That's it. Okay. So we'll do MPXX, MPH, -3, -I. We'll do include of this SSLABS /include. That's it. Good. Then we'll copy the actual thing and then link the libraries. So SSLABS. Or CAD. Grids also you include because the triangle and all those are defined in grids actually. And you can include the specific CAD functions, which are like STL holder and all those things. So that will be again SSLABS and lib. Oh, okay, sorry, yeah. Now the important thing is, since it's this very specific CAD function, you have to use CAD namespace also. So it's like STD things that you use, Chrono or something. Double namespaces. Oh, sorry, what? Why did I do this thing? Oh, what? What is there? SSLabs CAD has not been declared. Have I not included that SSLabs CAD? Oh, wow. I forgot to. I have to include SSLabs CAD also. Not IO, SSLabs CAD. So you can remove the IO. We're not doing IO, of course. No VTA, right? So just CAD. Okay. So now let's quickly list down the triangles. We have to pass the name of the triangle, name of the STL. So we'll quickly call which one? The cube STL. So examples, assets, cube, STL. Nice. So as you can see, if you open up the STL file itself, you can see that it will be the same. Okay, these are the triangles, vertices that are there. And the name of the patch was mesh. So like this, you can read triangles into a data structure. Read triangles into a data structure and manipulate them also. So if you really want to manipulate them, I'll show you an example. Suppose you want to add more triangles to this patch. What do? STL.add. So I want a new patch name. I will call this circle. And I'll add a new triangle. So how you'll see how to create triangles is basically a three-dimensional triangle like this. That's not three-dimensional, like a three-dimensional triangle means the vertices are three-dimensional coordinates, and then you call r-chords, three-dimensional r-chords. This is a good place to start using namespace because it's going to be otherwise very big. So you can add 1, 1, 1, and what else? Records. Or you can create temporary variables and as V0, V1, V2 and keep using them. You might be able to reduce the space taken by. There's a triangle, right? There's a triangle in 3D. So now if you want to write the triangle, this new triangle into some new file, you can just do write STL to my new triangle, my new STL. Okay. And you'll see there's an extra patch there. And if you see on, let's try to create a weird little self. Hope this works. Forgotten the syntax exactly, but oh, sorry. So quickly look at the syntax. Triangle. Triangle. ST triangle. How do you pass? You say you create a triangle by passing. Where's the constructor? Huh? Not this one. Constructor is okay. So this is a list, initialization list. So just put a. So basically, it's a little better to use independent variables themselves. Okay. One more error. Yeah. So okay, STL, yeah, there's a very important thing. So when you're writing back the triangle, you should also mention the STL scaling that should happen. So as you know, we converted the triangles in the file using some scaling factor. Now, suppose you want to write it back with the same scaling factor, then you should use it. So basically, now, if I was using STL units of 10 to the power minus 3 scaling to read it, then if I want to write the same kind of file, I should write it back in the same STL units. That is a required parameter because again, you don't want to mess up with the value conversions and so on. So right now I'll just use one. I can run it. And so we printed, and there should be a printout calling saying my new STL. It says solid circles, and it ends the solid circle here. This is one patch, and then there's a solid mesh patch. Okay. And if you open it, well, Paraview won't. I don't know how Paraview will render random triangles, but let's see. See. That new triangles that you added have come up here beside the cube. Okay, so you can edit and add modified triangles also in the STL.
You can remove also, right? You can
remove also.
Okay.
So if you want the, where is it? Remove, let me quickly check. What is the syntax? Where is it? Still holder. Oh no, right now I don't have remove. So the way we were temporarily doing it is you create a new, but I can add, see the problem is remove, how will you identify which triangle you want to remove?
Yeah, that's what I was about to ask. Like you have to get it from the, I mean, you have to read the STL and then that information is there.
So basically, no, see the thing is this, these triangles in a STL technically don't have any ID. Integer ID or something like a unique identifier. It's basically the list of vertices. Now vertices are real numbers.
Right.
So you can't do equal to comparison without losing some problem with precision and so on. So if we read in STL holder some unique ID for triangles, that is also a bit difficult because you are arbitrarily creating a unique ID for them. And there might be two triangles which have different unique IDs. Which one of them will you delete and so on. Yeah. So basically currently what we were doing was whatever triangles you want to include or keep, you just create a new STL holder and transfer them to that, add it to that. Then that new STL holder basically contains. So, or if you don't want to create one line by line, you can create a vector of triangles and add it to the, like same thing. Add patch name, comma, vector of triangles instead of single triangles. Okay, STD vector of triangles. That is also allowed. Okay. So, and you can dump it and write it. So this is how you use STL holder. Now that we have a triangle in memory or STL in memory, how do you create a marker grid out of it? So here we will use area and geometry brushes to show how those two things are different. So what we'll do is we'll create a marker grid. Or just define a marker grid, let the STL to marker algorithm create it as it wishes. And you'll guide the STL to marker algorithm by providing some brushes to tell where to create blocks and so on. That's it. So this surface representation of STL is there. Now you want to create a grid. So okay, no need to use this. And we'll keep hardcodes will keep losing up. Now, as I understand that this triangle, this cube per se, is between 0 and 0, 0, 0 and 1, 1, 1. Okay, so I'm going to just hard code some numbers so that the example looks cleaner or easier, simple enough. Otherwise, if I start putting scaling factors here and there, it will become very complicated. So what we'll do is we'll create a grid of scalar block. You could just pass a block to a STL to marker thing. You technically can. It's just that to marker. Just that we didn't have, apart from very unit test cases, there was no use of it. That's why I didn't expose it to the user. But let me check quickly. I think you still can. Scalar block. There should be something with just a block. No. Yeah, it's only grids are exposed, not the STL to marker function, which internally we use STL to marker on a block level itself, but that's not exposed. If you want such a test case for yourself, we can expose it. So anyway, let's continue with the block business. So usually STL to marker, this marker is usually standard size t, unsigned integer, because it can take any values from 0 to what? 10 to the power 18 or something like that. That means you can have that many, you're allowed to have that many parts in your STL, something like that. Again, as I said before, there will be 3 here for the dimension of the grid itself, and then a transfer data type for the MPI thing, which is also this thing. This is my marker type. So if you want, you'll see people are defining this as using marker type. Is this. And then this is just to make the code cleaner and fit inside smaller column widths. So marker type, marker. Now I'll have to tell it what all are the sizes of my blocks and all those things. So my grid will contain how many blocks? Let's see. So auto will just hard code for now. This is the num blocks. We'll say, let's have 4 by 4 by 4 blocks. That's some size. Or if you want like a simpler thing, 4. And then you have block size. And let's say we'll say each block will have 10 points. Is it 10 real points? You need to have one padding point also for marker. So our padding point will be numpad. Well, padding point will be.
This block size is has only like all 3 numbers are the same, right? Should be the same.
Need not be. No.
Need not
You can, no, need not be. No. Yeah. You can have rectangle cuboidal blocks. Means,
Oh, okay.
yeah, you can. No, see, for example, for the 2D case that we were doing, like pseudo.
Oh, right. Got it.
3D.
Yeah. Understood. Got it.
So num blocks, then block size. Remaining things are by default. Oh no, so here it is very important to give the min max, because now the triangle will have certain real coordinates, right? So now depending on where your armin of your grid is, the triangle will either fall inside your grid or it will be way away from your grid, you don't know. Okay, so let's quickly check what are the arguments for creating a grid. So we'll go to grid, we'll see grid says num blocks, block size, periodic. Okay, so we'll just say for periodic, we'll say it doesn't matter actually. You can say periodic is not required for markers. By default, wherever periodic is not required, you can leave it aside. Otherwise, periodic by default means that you have to do much more copies across large distances across the domain. So basically, from here this end to this end. So you can save on some time if you don't allow periodic. And resolution, that is an important thing. That is actually the most important thing when it comes to all these discretization stuff. So since the cube that we are going to discretize, that is roughly around 1 real unit in length or 1 meter in length, we will say ki, let's put a resolution of 0.05. That way it will have 20 points. But if you have 4 blocks like this and 10 points per block, you'll have 40 points. So only half the block size will be containing the cube or something. So we'll see, we'll keep changing it and see how much we get. This is what will determine where the block is actually located, offset compared to the grid minimum. So armin of the grid, we'll keep it at, let's say, minus, so usually you put some multiple of resolution, but okay, fine. We'll say it's at minus 1.1. Let's see where it creates. Then we'll just fill it up like this: periodic, then res, then armin. Those are the arguments. Forget about the STL index, that you don't have to care about. So this is how you create the grid. Now you simply have to call STL to marker function on this and pass the STL holder. So what you do is, it's a CAD function. So namespace CAD STL2. Now you have to tell what kind of a grid you want to create. Is it a SC or BCC grid? So it will create such a grid accordingly or blocks accordingly for you. What kind of a block? SC or BCC block. So the first argument is it. So let's see. So whenever you are confused about what are the functions, what are the function signatures, just search for these functions. So STL to marker, the SC marker says STL marker. These are the 2 arguments. Then communicator. So again, I have not been maintaining the non-MPI version of CAD because no one uses CAD nowadays without MPI. So any code that you're writing just for dummy showcase, just keep using MPI, because there might be some functions which are not MPI, but they might not have been maintained, so there might be bugs there. I have been meaning, whenever I get some free time, I will nicely segregate the thing, but that is apparently the lowest priority of developing non-MPI academic codes. So I've been strictly asked not to focus time on that. So what we'll do is here, we'll just pass MPI conversion, which contains the metadata of all the MPI communicator business. So, oh no, sorry, this is not the only argument. So you pass the marker grid also. This is the, so you have just defined the, declared the grid here, or like instantiated the grid here. The actual grid allocation, block creation, everything will be handled by this algorithm itself. So we'll see what that means, what the output of this algorithm is. So STL marker com, then comes geom brushes, area brushes, correct cap. Let us just use this for now and see what it gives. Then we'll come to the area brush and all those things. So once it will create the marker blocks and create markers inside it. Now then what we'll do is we will print the markers and see how it matches with the STL. Is it exactly, are the inside points falling exactly inside the STL, are the outside points falling outside the STL, and so on. So again, what we'll do is STL VTI writer, VTI, the name, this is where the name marker was coming from. Rank is 0 anyway, we're going to use only a serial process, not a full multi-process MPI thing. Then we will open file. Okay, open will basically contain the index of the blocks. So for this, I need the BIDX, and for BIDX, I need to loop over all the blocks. If you don't want to modify the blocks at this time, you can pass by reference to avoid a full copy, but you can say constant. That way it won't allow you to modify anything. Because technically when you're writing the block, you shouldn't modify anything in the block. It is constant. So this is the B pair, which basically means the pair of block metadata, which is B pair dot first will be your BIDX, and B pair dot second is the actual block. And how do you get it? From G, or for marker. Marker is the grid here. For marker, you will call B indices and blocks. Give me the map of that. So BIDX will basically, you can either write out BIDX properly or just call B pair first. And then you have dot add scalar block, where you have the second index, which is B pair dot second, which is the actual block. And here you will put ID, because that is the ID you'll get out of the marker. We will print padding points also. So we will do B pair dot second dot get zone padded. Padded byte size. VTI close. And then if you want to collect all these things into a single VTM file, then VTM writer, VTM, and then you VTM dot write VTI. That's it. I think you need to pass. No. Let's launch it. The compiler tell us what errors we have made. Num blocks. Why does it say? Okay, there are two definitions of the same thing. Is it? Marker type is not declared. Why does it say that? Is the issue it's saying? See. No, tell me once. I didn't hear. Oh, okay. Using VTI error was not declared because we deleted IO, so we'll include IO again. Open is not there. No. Open file, close file. Is it? People who are used to VS Code and Sublime will be like, why don't you just use VS Code and Sublime? They recommend all the functions to you. But what to do? Good person.
Hey, do you have you must have said some nice VimRC and all, no? If you have something, can you share it?
I actually don't. The only VimRC, I just create a blank VimRC so that I don't have the default settings also.
Okay. Oh, okay.
Because the problem is I keep changing machines so frequently, no? I do not have any customized machine nowadays. Earlier, I used to love, that used to be a hobby, to theme my machine with all kinds of fancy customizations and so on. But now it's like, whatever machine you give, just give.
I understand. Like working on many machines, yeah.
So, yeah. Okay. So now if you look at the paraview output of how this marker looks like, I don't know. So it apparently has created some blocks. I don't know if I can increase the line thickness, but okay. Let me just bring a solid color here. Apparently it has not created a block at this corner. We'll find out why it has not done that. Okay. Wireframe. Oh, it seems to have created blocks like this. Then if you go to surface view, it seems to be, oh, solidity only. So we'll go to ID. What is this ID thing? It says, okay, it's very low, but I'll just read off what the scale says. It says 0 at this point, then 0.1, 0.2, 0.3, 0.4, then 1 at the top. Red is 1, blue is 0. So where is 1? So 1, if we go and try to take a slice, X normal, apply. So we see that some marker IDs of points have been generated, which are labeled as 1 here and 0 outside. Now, if we actually open the STL of that thing, you can see it exactly coincides with the place where we, like, sadly for me, this version of ParaView does not allow me to change the opacity. So you can try, if you have a different version of ParaView, you can try to change the opacity and see that indeed this is the place where it matches basically. Okay, exactly inside the surface it is 1, outside the surface it is 0. Or if you want to do a thresholding business and all those, that also you can do, which will give you directly only the part. So now the question is, why did this not create? So let's again see what where the cube was located. So as you can see, the cube, what is that cube doing there? So wait, we'll again take a slice. This is interesting. Okay, this will take the slice here only. Shouldn't apply it. So we'll delete this cube, take a slice, and then apply the cube. That will be better. Take a slice. Okay. And we'll open the thing and try to see. Okay, so this was the cube. And that other thing which was showing up there, let's draw only the outline of that. Sorry, why am I moving this? Okay, so this basically says that, wait. Why is this block missing? That is weird. What parameters do they set? Let's see. Okay, let's give a broad enough gap. I think this has to do with this one. It's falling within a few resolutions of it. So we will fill it with, suppose, we'll say that my armin is 0. This is the origin of the cube minus some res into 10 resolution. So 10 points at least we will go. And here we'll increase it also a bit so that there's no, but that isn't the case, but okay. Fine. All the weird edge cases have to come in during the demo. No, we have crashed out all proper edge cases in this algorithm. Like it has been there for 2.5 years now. So yeah, this is basically some misinterpretation happening. And you can put a surface here. So there are supposed to be 4x4 blocks. How many blocks are there now? There are only 2x2 blocks. Okay, this is an interesting case. So we said that the grid should have 4x4, or at least we provisioned for a 4x4 block wala grid, but it created only 2x2 blocks. So now the question is why? And this is where the concept of area brush and geometry brush comes in. So we did a provision for 4x4, but only 2 by 2 was created. So let's again open the cube and see where it actually falls. Wish I could change the opacity a bit, but it won't let me, so can't do anything, sorry. If you try to see this, it's inside the cube, so it is fine. So if I just do the surface thing of the IDs and take a slice here, you'll see that the cube is supposed to be exactly in the center. So this is a nice estimate. Now the question is, how can I create? Suppose I want to create some block here. The geometry is not there here, but I still want to create a block. So what will I do? I will take this region and pass it as a area brush to my function. So you can go back and see the function signature of what STL to SC marker takes. We're passing a grid. So you have to check what is the STL to SC marker doing here. It's taking geom brush and area brush. Okay, then let's cover geom brush first. Suppose you don't want to create blocks for the entire geometry. Suppose you want to create blocks only in the top left corner of the geometry, okay, or top right, bottom left corner, and so on. So then, how would you do it? You would, by default, if you don't pass any brushes, which is basically this default condition where there is 0 brush, then it will create geometry brushes everywhere, in the sense that wherever there is a geometry, it will try to create geometry. Now, if I intentionally pass a blank brush also, it will create the geometry brush everywhere, because it will say, if you don't want geometry anywhere, then why are you calling STL to marker? Then just create your blocks. No? So if there is no geometry and still you're calling a geometry to marker, then what kind of a thing are you doing? And so on. So you have to pass some brush if you need to use, some non-zero brush if you need to stop the area brush STL to marker from creating any block near the geometry. So, or if you want, you can ask it to create blocks near only a certain portion of the geometry. So let's do that. Only a certain portion of the geometry will ask it to create a block. How do you create a area brush, geometry brush like that? So there are things called brush, and it takes in a dimension, it's D. So it's a D-dimensional brush. The first argument is the bounding box of your region of choice, and the second one is usually the resolution level, not the resolution itself, the resolution level. Because in a multi-resolution case, in a structured code, usually the resolution jumps across levels are in multiples of 2 or 4 or something like that. So here you give the resolution level 0 or 1 or 2, 3. Basically, resolution level 3 means from the coarses level, it will be 2 to the power 3 or 8 times finer. So anyway, we are doing single resolution grid here. We're not doing multi-grid. So we will use a bounding box. Bounding box is what? It's basically a real box of dimension B which takes in 2 arguments, the min and the max of the box. So here we will say the box, this actual STL box goes from 0 to 1. So we will say we want the bounding box of our region to be created, area brush, geometry brush to be created from geom brush, we call it, to be created from minus 0.5 minus 0.5. Let's say okay, let's do it further. Let's put 8 and 8 here. So this is the, someone just came. Oh, okay, someone just. So our chords D, and pass it normally also. Yeah, if you don't want to do it this way, no, there's a simpler syntax. Make, is it? make box. You can pass whatever coordinates you want to it, and it will create that kind of a box. Here I want to create a real box, so make box double. And it'll pick up the coordinates. Okay, you can specify the coordinates here also. So this closes this closes this. So this will create the box, this will give the resolution level. Now the resolution level is usually a three-dimensional quantity also, because just let me show you what is a brush. A brush takes the bounding box, this R box, and the resolution level is basically a three-dimensional quantity because you can try to resolve along a particular axis only. So for example, if I want a multi-resolution case where from dx, dy, dz in the courses level, I want to go to dx by 2, dy, dz, not dx by 2, dy by 2, dz by 2. You can do that also. Okay, so you're resolving only along particular axis. So for that, axis-wise, your levels of resolution can change. So 0, 0, 0 is by default the course's resolution level. Then dx by 2 dy dz, that kind of a resolution level will be marked as 1, 0, 0. And then dx by 4, dx dy, dz will be marked as 2, 0, 0, and so on. So you have to basically tell what kind of a resolution. But here it's a default, I think, 0 only. So you can leave that brush thing there. You just specify the bounding box for a single resolution case. The resolution is by default anyway, single resolution. So we'll pass this geometry brush. Where is what happened? Oh, church. Editing the code here and running it here. Okay, fine. This is another level. Yes, sorry. So used to closing files, right? Error which says that, okay, this John brush. Okay, sorry, this is my mistake. So technically, you can add multiple different regions. So for example, we chose one quadrant of this, right? We can add another quadrant like this. So this was geometry brush 1. Geometry brush 2 would be something like, suppose from, I say this to what kind of, like another small region, which is a bit far away, which is say 0.5. We'll start from 0.5. It's there, but go only till 0.65. There's also a possibility. Although it won't cover anything, it will be in the middle of nowhere. So, but I'm saying like you can have different regions. So like this. Huh? So then you can pass a vector of such brushes. So essentially, your geometry brushes are actually a vector of brushes like this. My geom brushes, and I'll keep pushing back some. Or if you don't want to call them, create them separately and push them back, you can just put this, make it on the fly here itself. But since I've already made it, I'll push it like this. The containers. The list. That way, this list has the whole thing, and then I'll pass this geometry brushes. And because I have been using std vector, it's always a good practice to include what container you're using. So I'll include std vector as well. Okay, fine. Let me do it there. Still, it is picking up some error. It says signature of this. It says constant brush 3 and geometry brushes. Is correct only. Why is it showing an error? Oh, okay, okay. But where am I trying to push the geometry brush? What purpose? Can I push it in the marker type? Geometry brushes. And I'll quickly run it with this thing. Let's see how the cube has been generated. A lot of brushes, some of them, as you can see, are empty. The surface here. And we'll try to see where are these things are, what do you say? Where the actual geometry is. So we will go to split this slice view. See, nicely it came like this. You created only in one portion of the area. Okay, without so since you did not give any geometry brush explicitly in this area, although there were STL triangles in this area, like just the surface of it, it did not have any bounding box from geometry brushes, so it ignored those blocks and they were not created. If you want to see which all blocks were not created to get an idea, or not wireframe is not the best thing. Surface, no, that's also not. Maybe, yeah. So these are the small blocks that are created. So ignore the overlaps, those are because of the padding points that I'm printing. Otherwise, you can see that how many? 1, 2, 3. 3 by 3 blocks were not created here. So basically only the bottom left side was created. Okay. So this is how geometry brushes work. When you go to multi-resolution, you can resolve different portions of a geometry with different geometry brushes. So suppose top left of the car, I want very fine resolution, bottom left, I want lower resolution and so on. You can use geometry brushes to change resolution across a geometry also. Now the question is, what about area brushes? So if you go back to your code and hit this, now suppose I want to resolve some area where there need not be any geometry, but I still want it to come into picture. So what can that kind of an area be? So if I look at the armin, so let's explicitly write the armin now. It's 10, no, so 0.5. Okay. So it was being filled with 0.5. So minus 0.5, okay, to suppose the box is from 0, 0, 0 to 1, 1, 1. So from minus 0.5 to minus 0.1, there should not be any geometry. But still I want to create some blocks there. Right now it was not being created. So if you, again, if I quickly go back to the view thing and show you the data extent of the blocks that were being created. So I will do the data axis grid. And if you, okay, it's too small, but I'll read it for you. Currently it is being created from minus 0.5 to, so in single resolution cases, if you don't pass anything by default, it will try to create all over the place. So it's being created from minus 0.5 to 1.5. That is the block extent. So let's create a small block somewhere. Usually all these block area brushes and so on are very useful in multi-resolution. That shows its true beauty. Single resolution, it's a lot of, yeah. Like you're trying to backfit a utility from multi-resolution cases to this thing. So basically area brushes, okay. Area brushes will be brushes, same kind of thing again. So you create your area brush. And we'll create a ridiculously small brush. Huh? Let's see what happens if you create some random. Suppose I go from minus 50 to minus 40 or something. So which is completely out of the domain. What happens then? What does it create? It won't, basically then it won't take anything by default. Because by default it will try to create everywhere. Okay. This is my by default area brush one. And I'm pushing this to, where am I pushing this? And I'm passing this area brush onto my algorithm. I did not put area brush, is it? Oh, okay, sorry. Yeah, right. So if what happened here again, let's look at the data access grid. From where to where is it being created? Minus 0.4 to 0.4. Where is the cube? Actual cube. We should take a better example. We should take a big domain, very small blocks, and then do this. Sorry. Examples. Okay. So the thing is, there are some extra blocks being created on the sides of it. Change the example a bit. It's again not the best example. So what we'll do is, let's work backwards once. Let's just create a huge number of blocks. Just give me 1 minute. Where does it go? Still do area brush. Still do a C marker. The C marker will be here. Create blocks. Okay. Just give me 1 minute, huh? I'll just check what is the default behavior. I've forgotten what the default behavior is. Some weird default behavior. Still blocks for STL and regions. So this creates STL blocks for regions, marker, counter brushes. Okay, let's do it separately like this. We'll not go through the STL algorithm. Let's try to just create blocks first and see what the behavior is. That will make it much clearer actually. So we have this marker type. Now what we'll do is we'll just say add, create blocks for regions. We're passing the marker ID, a marker structure, and the MPI com world, and the area brushes or the region brushes. Okay, and then we'll print this thing. So the thing is now it will create, but it won't have anything to allocate. So what we'll do is whatever is being created, we'll just allocate them here so that there's something to print. Otherwise, it'll give segmentation false saying that I don't have anything to print here. What are you asking me to print in VTI? And we'll fill with 0, for example. Let's see what it does. Minus 0.5. And then paragraph. Where did it go? So light now. What? It's there's nothing. Okay, let's delete all these markers. Do it. There's nothing. There's no markers being there. There's a marker.vtm, but the marker.vtm doesn't contain anything. Why is that? The reason is, as you can see, we created a grid of this from 0.5 to whatever the extent is, but the area brush we passed was nowhere to be seen inside the domain of the grid. So no block was created. Okay. And we did not pass any geometry thing also. We're just trying to create a region block. Okay. So now just let's quickly bring in the area brush into the purview of the domain. So what is our domain? Our domain, let's make this a bit more cleaner. Suppose we'll say our domain is from -0.5 to 1.5. And if it has to be to 1.5, we'll say that our block size is 100 grid points, and roughly if it has to be 0.2 then. This will, our max will is of the entire grid will be 1.5, right? If this is the case, this is fine. This is fine. So from 0.5 to 1.5, we will try to create somewhere in between a small patch region. So let's say we try to create from 0.5 to 0.5. That's the region. Whatever blocks falls in this small bounding box region, we will create blocks. Okay. As you can see, I'm just using create blocks for regions. There is no use of geometry brushes as of now. So technically we can just comment it out. So don't get confused, let's comment it out. Just one domain and one area brush we are using. So now if we compile and do this, we have these many things coming up. What are these blocks? Let's see. Marker. Okay. What is the extent of these things? Let's do a data axis. If you can't see, I'll read it for you. It's from 0.5 to 1.05 or 1.1 basically. So basically that is the offset of this one basically ends here in the middle of this block. But since even a small area is intersecting with the bounding box, this block will get created. And this is the overshoot of the block because of the number of grid points it has and so on. So area brush works like this. Even if you don't have a geometry, just if you give a bounding box on your thing, on your grid, in something which is inside the grid, you can create a series of blocks in that region. Similarly, let us independently find out what happens to geometry brush instead of this kind of a area brush. We will uncomment here. We'll create, so now we'll have to bring in the marker itself, the STL itself, and we'll call cat create blocks for STL. So let's search what is the argument list of create blocks for STL. In the cat function, both of these are being called simultaneously, that's all. First the STL, then the geom brush. The combined effect of that, except that the cat function has some default settings, which might be a little non-trivial. So I might change a bit also. If it's becoming too non-trivial for me only, So you can see it takes STL, it takes the marker brush, communicated brush. Okay. Corrupt margin, leave it. That doesn't, that you need not bother about right now. So we'll pass the STL. Okay. We'll pass the marker grid, pass the communicator, MPI com world, and the brushes, which are in this case geometry brushes. And what are the geometry brushes? Let's see. We want to create the brushes blocks only where there's a geometry and in the region. Let's make this a bit smaller. That way it's nicer to identify whether we are correctly creating something or not. So we'll say 0.1, 0.1, See, resolution is 0.2. So let's say 0.2. It's a very small region. We'll try to create geometry brushes. So resolution is 0.2. Okay, this will. Okay, fine. This will basically cover one block because if the resolution is 0.02 and each block is only 10 points long, then each block's width is 0.2. So this will try to cover only half a block. So it's okay. Any small intersection that the bounding box has with a candidate block will get covered. Similarly here, we'll try to do from 0.6, 0.6, 0.6. So with this kind of a bounding box or geometry brushes, you expect two disjoint cubes. One near this region, one near this region. So let's try that. By the way, what is the actual better view. Where is it? Who created first of all? That's the first question. Let's quickly delete all the marker IDs and run again. So there are no markers. Why are no markers being created? Still resolution. What is the problem? What seems to be the problem? So this is the bounding box region, and my geometry should be somewhere here only. Oh, obviously. What a idiotic thing I did. So this region is inside the cube, not on the surface of the cube. Inside the cube, anyway, there are no triangles. It's not a solid cube. It's a hollow cube. So it won't intersect with any triangle. Obviously, it won't find an intersection region. So we have to make it intersect. So to make it intersect, let's put minus here. This will cut a surface. That's good enough. And here, what we'll do similarly, we'll put something like this and 1.1. This cuts the surface because the cube itself is from 0, 0, 0 to 1, 1, 1. Okay, now it should create something. It is created. So this cases should be done properly. So at these cases, okay. It looks as if it has created a lot of blocks inside also, but technically I don't think it is inside. If you see a slice view of this, okay, you can't slice. You can take a slice of this. Take a slice of a solid thing. Can you see inside now? Okay, take a slice. Nicely coincided with. Okay, as you can see, it has created, and where is the cube? Wait, what was our region? That is weird. It should have created two separate things, no? 0.8, 0.8, 0.8, 1, 1, 1, and it's 1.2, 0.2. Units are fine. What seems to be the issue? Let's see, what is the data extent of this? It's creating the whole creating from minus 0.1 to plus 0.1. That is weird. Maybe anything really stupid I'm doing here? This is very weird. Why is it doing like this? It's really weird. This is the Z normal, right? I think. Geometry build, After 0.2. So this is minus 0.1, this is 0.2. So it should have ended. Wait, what is this weird number which is coming? No, it's correct only. Okay. 0 point. Yeah. So it should have ended here and this should have been truncated here. The question is, why are these other blocks forming? Something else is also coming in. Yeah. Okay, this we will see because I think most probably what has happened is that function create STL blocks STL. We'll find out what exactly is going on. Okay. Okay. So, what is happening is that these blocks, no, they are trying to push the entire thing onto the thing. Why my T brushes was not zero? No? What did I pass? This is apparently C. Basically, when I'm passing a grid, it is creating this problem. Okay, we'll see. See, no, there is something stupid I'm doing because in all the cases, test cases, it works and so on. Fine, this is a bad example I'm choosing. I have to get back to something else on this. Geometry brushes, geom brushes. I'm think clearly. Okay, we'll get back to this. I'll figure out what the example is trying to do weirdly and then I'll resolve it. We'll talk about this later. Okay, fine. Now, coming back to what are the other features? Patching. Let's do one thing. We'll take a, is there a marker file which is leaky or something? In the examples, or do you have one? Oh, it's there in the this thing, no? Issues. Suppose the other feature which is there in this is patching leaky STLs automatically. So let's look at removing negative space. So suppose I just take you through what the problem is. So in many cases, you will find that your STLs are leaking. So basically there are holes like this in that. So one thing is you can ask the client for giving you a filled STL file and then, sorry, just 1 minute. You can ask the client to give you a filled STL file and then you can try to again do your simulations on that. Or if it's actually a very complicated geometry and even the client is unable to fill and so on. So there is this STL patching algorithm. So the first thing the STL patching algorithm does is you have leaky STL, it will find out where the possible holes are. Now a hole can be a feature or a bug or a leak, actual leak. So the algorithm doesn't know whether a hole, it will detect a hole, but whether it's a leak or a actual feature that you have to say. So basically, if you know, it will tell you that these are the locations where the holes are. Do you want to patch them or not? If you say yes or no to each of the possible leaks, then it will identify the hole and then patch it with a patch like this. So this can be used to patch different types of things. So if you just want an example, I'll show you. So you will just copy paste this example. pass into the RGC. I'll just take you through what is going on exactly here. So, yeah, GB1. So this is standard. Now, what we can do is we can start finding holes. So to find holes, there's a simple function called find holes. So let me take out an STL which is leaky. For example, this one, the one which we are seeing in the case. Negative. Where is the STL? Oh, it is not here. Can you operate somewhere? Then I'll take it down. So if I open this in ParaView, you'll see that there are these multiple or single hole. Oh, it's okay. Yeah, okay. So there's one hole here, and there's one hole here. There are essentially three holes like this. So suppose all three holes are bugs, like leaks. They're not features. Then how do you automatically patch them? So what you'll do is first you'll load the STL, we'll load that. Then essentially this group type will give you, so find holes, if you pass the STL, it will give you a group of edges. What is a group of edges? It's basically the okay. A hole like this will have triangles which are surrounding it, which do not have a neighboring triangle. So basically for each triangle in a very compact, closed, like a non-leaky STL, every triangle will have neighbors. Okay, it's not like one triangle will just come and end at a arbitrary surface. It means by definition STLs are like that. Okay, it has to be a closed surface. So basically whichever triangle doesn't have a neighbor, it means there's a possible candidate leak. So basically the edges of the triangle which do not have a neighbor, those form a ring like this, and those are the lines surrounding the leak. Now there can be multiple patches, so there can be multiple such groups of lines. So what you can do is, the argument, this find holes, basically what it returns is, it will return all those groups of lines and a vector of them. So edges type is basically one group, okay, or one ring. And it will send you a list of them if there are multiple patches. Or if there's only one patch, it is a one element list or so. So you define the temporary container which will hold those list of rings, and then you pass it to find holes. Okay. So in this case, if I just do find holes and print how many holes are there, all G size, after calling the find holes SQL. In this case, it should give me, it's not this one. In this thing, where's the other one? Oh, closed it. Okay. This should give me three lists, three groups of rings. So let's see and run this. The remaining parts of the example I'll come to. I'll just comment it out for now. So, wasn't that, is it? So this one. Move. Nice. So I'll just pass this, compile this patches. So, patch holes. So let's see. We'll be passing the file that we downloaded here. So it says 3. So there are 3 groups of rings it's identifying. Now, if I go code again. Sorry, not this one. So we have found 3 holes. Now the question is, which one do you want to choose and patch? So for example, what we can try to do is, see, as a rule, what it will ask us to do is, we will just one minute. Apart from this find holes function, you have another function called create patch, where if you give the triangle, give this function one particular ring, it will create the patch for that ring. So basically, if I give it this ring, for example, it will create a circular patch and give back to me. So here, what essentially we are trying to do is, we are trying to iterate over all the patches, and or at least the first 2 patches, and then create rings only for patches only for those 2 rings. Okay. So let's do this. So here, what we have done is, all G contains all the rings, list of all the rings. From there, we are choosing only the first 2 rings. Third ring will keep as leaky. And then we'll pass this list of triangles, which will form our patch. So basically, for each of these rings, which is the sub G size, we will create the patch and store it in the list of triangles, and this list of triangles will add to the STL that we have. So basically, we are patching it in situ with a name called patch underscore whatever the ring name, group is. So basically, if this ring is called group 0, group 1, group 2, then we'll have patch 0, patch 1, patch 2, like this for the 3 patches. We're doing it for the first 2, so we expect patch 0 and patch 1 only. Okay. So now what we'll do is, so this is all programmatic. We will write also the STL to see temporarily how the STL looks like, the patched STL looks like, and we will also verify that the find it after doing this patching or adding the patch into the STL. When we do find hole, it should then show me that only 1 patch is remaining. All the other patches have been patched off.
So how do you choose the resolution, like that patch?
Okay, technically what it does is, if you have this ring of edges, it will basically form a polygon, right, in terms of the edges.
Yeah.
You just triangulate that polygon.
Okay.
So how finally you triangulate, that depends. Like, it will find a triangulation. Whether it's the best triangulation or not, that's the truth. Like, will it actually match the curvature of this body and all? Those are very different. It will match. How it matches itself. Because the idea is, the holes are supposed to be very small, so the local curvature will be almost flat. Yeah.
Okay.
Because if it is such a big hole in the geometry, then the geometry person has to be taken. Yeah. This is just as an example.
Yeah.
Okay, so how many holes are left here? So we'll do the all G size. As you can see, I'm clearing out all the rings here. Then we are afresh filling up all G. The find holes is doing it. So this is after. Remaining will comment out. And we'll write the STL also. So if we see, we'll try to see which all patches it has patched out. So not STL, sorry. STL dot write. We will write to patch 2 patches HTL. And applicable resolution units. So we'll just use the default units which are using here. Just one. Let's compile and run this. We'll do 3 first, and then how many holes are remaining? 1 hole remaining. Now let's look at the triangle, which is called patched. As you can see, by the way, Varivia does a nice job where it gives the patches in a different color. Means patches are loaded in different colors. So there is 1 patch, there is 2 patch, and the 3rd one is still empty. See? Nicely it has patched up. Okay. And then
Can I see the wireframe of it actually, just to get an idea of what it's doing?
sure. You can see the patches separately also if you just dump the patches as STLs by themselves. But I'll show you the wireframe. So this is all Ravi algorithm wise his brainchild. You can ask him, pick his head. So see, this is the patch that was generated. It's triangulated to pretty decent resolution.
Yeah, actually.
Yeah.
Although it looks, I mean, under result, but yeah, in white frame it looks good.
So we call the point on that surface and then Delaunay triangulation. Is it?
Yes, you can do Delaunay, but if you have a polygon, the simplest way to create a patch out of it is find the centroid and drop edges from the centroid to the edges. No?
Okay.
That's what it does.
But this looks like way more refined than
And this is empty. This looks way more.
refined than when you just drop from the center.
Oh, okay. No, I think, yeah. Ravi, that is what it's doing, no? But yeah, no, see, no, it's okay. Since there are so many edges, it looks refined. If you zoom in, no, you can see the radial thing. Edges
Yeah,
picking
okay.
up. So, and this will patch exactly. There won't be any leaks left after this. Look like Death Star, but okay.
Yeah, keep seeing.
So yeah, and then if you want to patch it fully, then you basically pass all the, sorry, this one. And if you want to patch fully, then you can again patch like all of them. So push the other one also, whatever was there. So that will ensure that you have zero patches, zero this thing left. So if I 3 patched now, we patched all 3 of them. Okay. 3 and 0. Okay. And if you want to see again the wireframe, you can imagine what it looks like. Okay. 3 patched. Like just like this. So these are the features which are there. What time? It's 5:30. Okay. I think. Okay, now just tell me if there are any questions. Let us take it from there. This geometry brush and area brush, I'll create a better example and show. There's some weird thing I'm doing and screwing up the whole demo. Okay.
As you told, I think with multi-res, that will be.
Yeah, I think, yeah, mostly because again, it all depends on the use case. Like how many people are using which one. So yeah, but anyway, I'll check. Multi-resolution, it will be better, yeah, to see exactly how it works.
Yeah, otherwise, there's, I mean, what is the use of geometry brush? Sorry, area brush.
Yeah. Area brush, well, well.
Yeah, resolution will be same, no? So whether you create in weight or wherever.
So basically, you can use geometry brush to, what do you say, create, like suppose you want to do a, okay, I don't know, really, it's an academic example actually, yeah.
Okay.
Yeah. No, as in, yeah, single resolution, geometry brush, area brush. No, but these people want, no, this artery, you know. So there might be, I have to actually, no, Atif is using it very nicely actually. I think, is Atif here? He is the correct person to say about this thing. I myself don't use my library. That's why I'm the worst person to demo the use case. I can tell you about the internals, but the users should be the one who are telling about the use cases. So Atif uses it very nicely. Maybe it would be good to get a single resolution area and the geometry brush example from him. It will actually show how it works. Yeah. But yeah, otherwise, if you're doing multi-resolution, then yes, area geometry brush will come from your group. So, okay, Hannah, are there any questions? I know there are a lot of questions. And how many people are there? 6 people only. Hey, Bhagwan. Oh no, 24 people. Everyone is dropped off only. Like, oh, okay. So, then say, since, okay, I'll just stop it here. there are any particular points to be discussed in specific, we can start discussing one-on-one or in smaller groups and so on.
Yeah, that will be, I think, better because you have given a very nice introduction now, man, like to the core, and because you were writing down the code itself, it was nice
Yeah.
to see it actually.
Yeah.
Yeah, that was
Yeah.
that's really
See how many errors you get before it actually runs.
right. Yeah, true. Actually, that was good that happened, and I mean, you did that like that
Yeah.
because debugging now is not as scary as before because I know at least where it might be coming from and stuff.
Yeah.
At least a little bit. Yeah, I mean, these are simple codes, obviously, but yeah, it was nice. So many so in terms of MPI communication wise, you said it is the neighboring communications, right? Top SC communication.
Yes.
So, what requirement I had in one of the cases that we were simulating was that to take averages, span-wise averages. Sometimes you can take span-wise averages without by creating groups of processors, which are essentially group of blocks together, which have been converted into a MPI group, essentially, so that you can do the averages faster, basically. Otherwise, you have to loop through all the blocks.
Yeah.
So that kind of a thing, I wanted to know if there's something, or should I write an issue and stuff like that and go through proper procedure like.
No, right now there is no usage of specialized groups. Okay. So everything is almost like a free graph because the thing is, in the most generic case, you don't have any structure. Like you don't have any predetermined structure. First of all, if you're doing multi-resolution, see, previously till 2016, when we did not do multi-resolution, or till 2017 actually, or 2018, I don't know. We started doing multi-resolution very late actually. So till we were doing single resolution, it was always Cartesian grids. And we never used to delete blocks. Actually, we started deleting blocks and doing proper multi-resolution only in 2019. Okay. So till before that, it was always Cartesian topologies of blocks. Okay. So in that case, you had that MPI Cartesian topology, and that used to give you left, right, top, down neighbors, and that's it. There's no need for any separate MPI class or communicator also per se. It was like that. Then when we started doing multi-resolution or like deleting blocks and things like that, then it became very, very unstructured. Like you never know what the topology will be.
Okay, got it.
So then I based there's no pattern or network connectivity that you can predict. Later on, yes, you can optimize on that and make a local graph topology with well-defined neighbors and so on. But then AMR will come and ask you to change that also.
Okay. A lot of once you add these many things,
Yeah.
I understand.
So that's why it was created as a very global, unstructured graph kind of topology, making sure that we do local clustering in load balancing such that there are not too many long distance communication going on.
Okay. So that's how it is. Okay.
Yeah.
And one other follow-up sort of question. So let's say you have the domain, and I have velocity field and everything, and need the kinetic energy, the global kinetic energy. So you do some reduce on all the procs, which have the blocks, right? So, but when you go through that for loop, which has that thing, that ampersand pair, that basically that's a different kind of for loop.
The iterator is for.
The iterator, it's called the iterator. Okay. So there you mentioned that it goes to random blocks and
sequence. Yeah.
Oh, so that sequence is actually random only then?
Yeah.
Okay.
Yes, if you print out the sequences 2-3 times, it might seem it's following the same sequence, but it's actually random.
Okay.
Because there's no guarantee that one will come before 2 and so on.
Okay.
Just on the last question. Oh, sorry, continue.
Yeah, no. Tell anything. Yeah. Okay.
So you were saying, when multi-resolution was not used and there is single resolution, MPI Cartesian, that topology was used.
Yeah.
So in order to just do so the send-receive business is not needed when we don't have that complex block topology, right?
Oh no, send-receive you still have to do. Just that the syntax will become a bit simpler. That you don't have to go searching for the neighboring rank, trying to figure out on which processor even does my neighboring rank exist, because you know that my rank So your rank, first of all, will be a three-dimensional coordinate itself. It won't be rank 0, rank 1. It will be 0, 0, 0, 0, 1, 1, 0, 0, and so on. Then automatically you will know that rank 0, 0, 0 will have block 0, 0, 0.
Correct. Okay.
And block 1, 1, 1 will be on in rank 1, 1, 1. So basically now if I am trying to update the neighbors of, suppose, block 1, 1, 1, for the negative x phase, I will need the data from 0, 1, 1.
Correct.
I don't have to maintain a separate list and back calculate where that block exists, on which other processes this block exists. I know that automatically by the block ID itself that it will exist on rank 0, 1, 1.
All right.
So basically writing in MPI sentences become very easy. And actually, since you've already defined this is the topology, it's a bit faster also in terms of hardware thing, communication.
Okay.
But you cannot afford MPI Cartesian topology for arbitrary geometries. So what to do?
Samit, you had actually already explained, but I forgot. So, where is this performance bottleneck for multi-rest thing? I kind of guess it's very difficult to optimize, but is there a way out now?
See, the thing is, when we profiled the ML body code, we found it is 2x slower than theoretical.
Okay.
The biggest bottleneck currently, which is not expected, are in two places. One is, I think Chakri is working on, is the course find refill some part. And the other one is the intra-level communication. Okay.
Okay.
Now, why is the intra-level communication suddenly becoming a bottleneck here? The reason is this. See, if you have a very large...
Intra is basically that communication inside a NUMA node, right? Like that.
By this intra-level, I basically mean the communication within blocks at the same level. So it's a simple single level resolution send receive kind of thing. Why is that becoming a bottleneck? So turns out it's actually not MPI communication limited. It is still memory bandwidth limited because of this. See, if you take a very large block, the number of surface points that you will have is 6n squared. And the number of bulk points you'll have is n cubed. So when you do MPI communication, first you have to pack those surface points into a buffer, send the buffer over MPI, then unpack the buffer into your neighbor grid or neighbor block. Now, if you actually write out the number of operations taken for this surface points to be packed into a buffer and then unpacked from a buffer into a thing, you will see that there will be 6 phases. Then for each phase, you will be, suppose there's only one padding point. Then still the buffer number of surface points will be, suppose you're packing along minus x, it will be 1 point along x direction, but there will be full nx plus p 2p and nx plus nz plus 2p in the other directions. So it is the number of points is basically almost n plus p squared, where n plus 2p squared, where p is the number of padding points. This calculation is actually given out in one of millions repos, but okay, I'll just explain verbally once. If you do this calculation for very small blocks of size 20, 16, and so on, 18, you will see that theoretically itself, the amount taken to just unpack is 2 times more than advection only.
Oh, okay.
We never thought about this problem because till again, when we were saying, before we were doing multi-resolution, when it was only huge 128 cube blocks and 1 block per MPI process, the surface area was so low, no one cared about MPI communication. But the moment this unpack pack business comes in for small blocks, it becomes the overhead. And that is where multi-resolution is getting bottlenecked. Means it was not in the theoretical estimates which we did earlier. It actually completely didn't cross our mind, this theoretical estimate. No, what I'm saying is in 2019. Now we know, we always calculate this also. But yeah. So.
But 2x slower is fine. So I thought actually it's much slower. But yeah, one thing is we actually never ran optimally in a sense that with 16 cores, we always used to run with 32 or 60 cores.
No, we properly benchmark this time. Kaushik will tell you all the harassment he has to go through in my hands. He got so nervous, or I'm not nervous. It's basically so many different things he tried out. He had some 7-8 copies of codes changed in his Rudra cluster. And we were completely confusing which code does what and so on. So I was optimizing a code which was apparently not supposed to be optimized at all, because it was the wrong code and so on.
Oh.
And so basically, after I optimized, I gave it and it gave segmentation fault. I was like, what did I do? And then after 2 days of debugging, I found out the original code itself was giving segmentation fault.
Oh my
And just
God.
as the code which he showed me was supposed to be optimized, he did not upload that. He uploaded the wrong code instead.
Oh.
So like this happened, and we had to stay up day and night, and finally we got it to a proper stage. Like first thing we told him or everyone is basically no multiple copies. One
Yeah,
code, one
actually,
repo,
yeah.
one branch.